Okay, good morning, everybody. We're starting the fourth day of the conference in honor of Fernando. So our first speaker today is Douglas Ulmer from the University of Arizona, who will speak about foliations and the geometry of complex elliptic surfaces.
Okay, good morning. Can you all hear me? Yeah. Thank you to the organizers. It's always a delight to come to the mathematical paradise that's IMPA here in the forest. And Fernando, congratulations. So I first met Fernando in 1983 when we were both first-year graduate students at Brown. He had spent a year at Chicago, so he came. He knew a lot of stuff that the rest of us didn't know. Very, very impressive as a problem solver, but also very impressive in his mathematical taste. From day one, he was really great at knowing which problems were interesting, which were beautiful, which were worth thinking about. And his influence has been very large on me in these matters of taste, both in mathematics and in life. He and his wife set a fantastic example of how to host people in their place, how to make everyone feel comfortable, and how to somehow generate a very warm and interesting environment. So, Nando, congratulations on your birthday. We're very proud of you. And I should say, I also had a chance to work with him later. We wrote a paper together, and I visited him a few times in Buenos Aires. And it's extremely impressive, the school that he's created around himself, and extending this influence of what ideas are worth thinking about. So again, congratulations, Fernando. It's been really great to know you. Of course, we're not done yet, but yeah. Okay, so I have just two slides. It's going to be a board talk, but those are the references. And I'm mostly going to talk about the second two papers, which is some recent project about something very elementary in elliptic surfaces with Giancarlo Urzua in Santiago de Chile. If there's some time, I'll talk about that first paper, which has a very interesting foliation in it, but it's kind of old news. I talked about it the last time I was here, so many of you have heard this story before. So that, only if there's a little time when we talk about that. So let me set up the problem. So I'm going to start with an elliptic surface, E, over some curve C, map here pi. So this is a family of elliptic curves. It's allowed to generate. In fact, I insist that it degenerate. The base curve is allowed to have any genus you like. The generic fiber is an elliptic curve, so there's a zero section here. So this is a so-called Jacobian elliptic surface, zero. And I give myself another section P of infinite order. So let me assume, first of all, that the J invariant of E is not contained in the complex numbers. That's the insistence that there are actually Bayesian degenerations. The other cases are extremely interesting, but I will leave them off for simplicity here. And let me define a couple of invariants here. So D is something that I might call the height of E, and this is the degree as a line bundle on the base curve here of the pullback of the relative differentials. So this is a basic measure of the complexity. It actually tells you the degree of the coefficients of a defining Weierstrass equation. Okay? And I'm going to assume that this P is not torsion. So P of infinite order. And under this circumstance, if you look at some multiple of the point, say n times P, and then you intersect with the zero section, the intersection number here is asymptotic to some constant times n squared. So there, as you take multiples of the point, it meets the zero section more and more often. And the question is just how transverse is this? Right? Does it happen that it's always transverse? Can there be tangencies and so on? And of course there can be. Let me just point out that a tangency here, so if you had a multiple, this intersection divisor was not reduced, so a tangency between n times P and O is an unlikely intersection in the projectionization of the tangent bundle of E. So I have a smooth surface. I have these two smooth curves. There's a well-defined tangent line at each point, so I can lift the section to a section of the tangent bundle. Now I'm up inside this threefold. I have two curves. They probably don't meet. It's an unlikely intersection when they do. When they do meet, that's precisely the statement that the section and the zero section or tangent at the point underneath the place in the tangent model. So the question is really how often does that happen? All right, and so in this game of unlikely intersections, what you do is inflate many times and see if you get something finite. So I'm going to consider a set of tangencies. So this is going to be the union over all n of the set of points t in the base curve, such that np and O are tangent over t. Okay? Maybe I should have drawn a picture here. I have my curve, some elliptic curves, maybe some bad things, zero section, and then this guy P. Okay? And so the statement is that this guy is finite. So there's only finitely many places where you have a tangency. And in fact, there's a remarkable formula for, or a remarkable bound for the size of this set. So this is at most 2g minus 2. This is the genus of the curve, minus this height, plus delta. And I should have written over here that delta is equal to the number of singular fibers. And really the number, no multiplicities, no valuations of delta. They're just the physical number of bad fibers. So you get this remarkable sort of topological formula for the number of times that you can have a tangency here among all multiples. And I want to try to explain this formula, and there's a foliation in the background, which I think is pretty interesting and has had some other applications. So statement clear, I hope? Yeah. Okay. So let's start figuring out why this might be true. So I'm going to, I have my elliptic fibration. And inside here, I'm going to take the set over which pi is smooth. So I'm just removing the bad fibers inside here. So let's call this guy pi 0. And I'm just going to remark that, so this is now really a family of elliptic curves. No degenerations here. I've removed them. And there's a group law on the fibers of this guy. And I want to consider what the torsion points look like. So I'll write E0 of n. So this is the union of the n torsion points in each fiber. And this maps down to C0. And this guy is atoll of degree n squared. Okay? So you have n squared torsion points in each fiber. They move around. They mix as you move around over the curve, but there's no collisions between them. It's an unramified cover of degree n squared. And as you vary n, you get an everywhere dense set of points, right? The torsion points in each fiber for higher and higher values of n completely fill out that fiber. Well, they fill it out. They're everywhere dense. They don't fill it out, but they're everywhere dense. And it turns out that you can complete this family of atoll covers into a foliation of E0 that's quite interesting. And it's not a holomorphic thing, but it's nevertheless very interesting. So this, so let me say some things here. So as n goes to infinity, E0 of n is everywhere dense in E0. And the remarkable thing is that we can complete it to a foliation of E0. Okay, so to do this, let's give ourselves a little disk inside, say, a classical. Everything here is a classical complex topology. I don't need this risky topology at all. I'm going to work with these things as manifolds. I'm going to take a little disk here and look at pi 0 inverse of this disk. So that sits inside here. And this is very nicely described by Kodaira a long time ago. So this thing we can write as the set of pairs Z and W, where Z is in the disk, and W is an element of C modulo Z plus Z tau of Z. And here, tau is a period function. It goes from this disk to the upper half plane. Okay, so I'm just uniformizing each fiber in a little disk. I can do this in kind of a uniform way with a holomorphically varying period. And the thing that I want to observe is, let's see. Yeah, I think I'll just go over here. So this thing is also equal to, or isomorphic to, real analytically isomorphic to the disk cross R mod Z squared. And the map here would send a Z and two real numbers R and S to here, it's the same Z. And then I would just take R plus S times tau of Z. Okay, so that's sort of stupidly a bijection between the two sets in question on the board here. It's a real analytic map. It doesn't look so non-holomorphic the way I've written it, but let me write down the inverse here. So if I had a pair of Z and W, then I would map that to Z. R I'll tell you in a second, and S would be equal to the imaginary part of W divided by the imaginary part of tau. And then this would just be W minus that. So this is S, this is R. Okay, so written like that, you see that it's clearly not a holomorphic thing, right? It's a real analytic thing because I've got these imaginary parts in there. So we've slightly left the world of complex geometry, but nevertheless, this is an interesting thing to do. So what I want to do then is get the right set of notes. I want to observe that this local presentation leads to a global foliation. So we define local Betty leaves. This in this set here. So in pi naught inverse of delta as the sets with fixed R and S. So I let Z vary. I fix two real numbers R and S. When I look upstairs, and I just look at this thing, and it's a section over the base, right? And then I can glue these together by analytic continuation. So glue by, I mean, it's not even analytic continuation, but just overlapping. I'll write that. But. Okay, so what's the nature of this thing? So let's notice that the global leaves are indexed by R mod Z squared modulo gamma, where gamma is the monodromic group. It's the image of the fundamental group of the open curve at some base point, acting on the automorphisms of H1 of the base point Z coefficients. Hope that that's got the right number of parentheses. One more. Okay, so you take some little leaf, which is constant R and S, and you follow it around, and the monodromy takes you to some other leaf when you come back to that disk that you were over with to begin with. So it's indexed by this funny set, and the closed leaves are indexed. Well, they're indexed by the situations where the orbits here are finite. That turns out to be Q mod Z squared mod gamma. So in other words, if R and S are rational numbers with common denominator n, then the corresponding multi-section consists of all of the n torsion points, and that's a finite closed thing over the base. None of the other leaves are closed. These are the only closed leaves. The other guys are dense everywhere. Okay? Okay, so this foliation turns out to be pretty useful for a lot of things, actually, but in particular to study the problem that we've set up here about these tangencies.
Is this a non-singular foliation?
Yeah, so the leaves are holomorphic submanifolds. They're not closed. Yeah. Okay, so what turns out to be the case is that, so in the end, so we defined this set of tangencies, right, which was the union over all ends. I'm going to call this the torsion tangencies. Set of T in C such that n times P tangent to O over T. And let's just observe that this is the same thing as the union of the points in C, such that P itself is tangent to an n torsion point. Let me put the open thing in here just for a second to avoid any confusions. Okay, to say that n times P is tangent to the zero section is the same thing as saying that P itself was tangent to an n torsion point. And now I just want to relax this a little bit by, instead of looking at n torsion points, looking at the leaves of the foliation and ask what about the tangencies there. So this guy is contained in the union over, say, R mod Z squared mod gamma, so the index set for the leaves of the foliation. I don't even need this, let's just do this. So T in C0 such that P is tangent to a leaf of the Betty foliation over T. Okay, so bigger set, but now it's better. I'm covering the whole space. I can expect a little bit more uniformity here. I've taken away the arithmetic. The n torsion is sort of an arithmetic thing. I've enriched to a foliation of the whole surface, and now it's something that's a purely geometric construction. Okay, and so this is a thing that turns out to be easy to bound, or easier to bound anyway. Okay, so, and I'm going to eventually show, so let's call this guy T Betty open. And we're eventually going to show that the number T0 Betty, actually there's a non-open part of it which I'll define a little bit later, and this is going to be less than 2G minus 2 minus D plus delta. Okay, so let's start towards that bound. So I'm going to define, let me say a few words about the foliation near E minus E0. So in other words, near the bad fibers. I don't want to write this out, but let me just explain in words. So put yourself near a bad fiber, and I've only defined the foliation away from the singular fibers. I haven't said what happens, and I won't really say what happens there, except for the following remark that many of the leaves do not specialize in a nice way to the special fiber. The ones that clearly do specialize nicely are the torsion leaves. Because there's a group law on the bad fibers. It's either the multiplicative group or the additive group extended by a finite group. And so there's a good specialization there. And it turns out that the leaves that specialize nicely all specialize to points in the closure of the set of torsion points in the bad fiber. So if you're in an additive fiber, the group is a finite group cross the additive group of C. So there's no torsion in the additive group of C, and you just have the component group. So some finite group of order turns out less than 6. At the multiplicative fibers, the group is a finite cyclic group cross the multiplicative group of C, lots of torsion there. They're the roots of unity. Closure of that is a unit circle, and the leaves that specialize into that fiber all land in the unit circle. Okay? So in particular, they do not hit all of the special fiber. Okay, so I'm not going to try to write that all down. Let me now say that we define for all points T in C, including the bad points here, an index I of P and T. So this is going to be bigger than or equal to 0, and it's bigger than or equal to 0 in general. It's bigger than or equal to 1 if T is contained in the open part. And in the open part, where you have T this guy, I of pt, is just equal to the intersection multiplicity in the usual sense of p and the Betty leaf that passes through the point P of t. Okay, so P is up here somewhere. We're over T. There's a leaf there, so there's definitely an intersection. So, and I take the intersection number there, so it's at least 1 and it's 2 or more precisely when we have a tangency. Right? So those are the interesting points. So IP of t is bigger than or equal to 2 if and only if P is tangent to the leaf. Okay, so you do something similar at the bad fibers, except there may not be any intersection at all. Your P may specialize to a point which is not the limit of a leaf, in which case we take the index to be 0. If it is the intersection, if it does meet a leaf there, then we just take the intersection multiplicity with the leaf. Okay, so for T that are in the curve but not in the smooth part, I of P and T is 0 if P of t not meeting a leaf, which is, of course, the right answer for the intersection number, and it's as above if P of t does meet a leaf. Okay, and so what we want to show is that the sum of this index P of t, so let me write this out better. Okay. So I think what we can say is that the number of elements T and C0 such that P is tangent to a leaf over T, this thing is less than or equal to the sum over all T and C0 of this index minus 1, right? You get a tangency precisely when the index is bigger than 1. And this thing is bigger than or equal to 0, so this guy is bigger than or equal to minus 1, and so delta plus the number above is less than or equal to the sum over all T and C of I of P T minus 1. Okay, so the count that I'm asserting something about is the sum of intersection numbers. Okay, so now as a next step, I want to introduce a sort of differential that's useful for studying this problem. So I'm going to define a real analytic, one form on E0 by the rule that eta, in the local coordinates that I described above, eta is going to be dw minus the imaginary part of w divided by the imaginary part of tau times d tau. So this, remember that we had a disk here with coordinate z. We had pi 0 inverse of that disk, and this was equal to the set of pairs z and w, where z is in the disk and w was in c on z plus c tau. Okay, so in these local coordinates, I get a one form here, and it's visibly not analytic because of those imaginary parts, but it's real analytic. And if you look back at the formulas that I wrote down relating w to r and s, you see that at some p in E0, if I take this form and look at its perpendicular in the tangent space, this is actually the tangent space to the leaf through P. So this form tells us about the local behavior of the foliation in a sort of a differential way. Okay, and then I define A to P to be equal to just the pullback by P of this form. So this guy turns out to be, this is equal to a real analytic section on C0 of omega 1 of C tensored with omega inverse, where omega here is pullback of the relative differentials of E over C. Okay. So then, using winding numbers, we can define an integer, j of P and T. This is for all T in C, which is sort of the index of A to P at T. So this would generalize the order of vanishing or pull of this thing. If it were a holomorphic section of this line bundle, that's exactly what we would get. You can, if you think back to your calculus or your bot 2, you can define this local index by doing a little line integral around a small loop around T. In particular, the form doesn't need to be defined at T. It needs to be defined in a neighborhood of T. So this gives a definition for all points in C, even the points where this form isn't defined. And it's telling me that if you were to continue it across this, if it were holomorphic, and if you were to continue it across this point, it would give you the order of vanishing or pull. Okay, and it turns out to be something that you can calculate. Okay, and so using this Kodaira description, or a Kodaira description of the group law on E0, you get a nice calculation of this guy. And the theorem then, so this is kind of the technical heart of the proof, is that for all T in C, all of it, not C0, this differential index, PT, is precisely equal to the intersection index, PT minus 1. Okay, so we plug that back into our formula, and we see that delta plus the number of points T in C0 such that P is tangent to the Betti foliation at T. Well, this is less than or equal, we already observed, to the sum T and C of I of P and T minus 1. And this is equal, according to this theorem, to the sum over all T and C, J of P and T. And I was actually kind of stuck at this point for a while. And then I remembered something from our first year topology course at Brown from Bottom 2, which is that the degree of a line bundle is a topological invariant. If you have not a holomorphic, just a smooth section of a line bundle with isolated zeros and poles, then the sum of those zeros and poles, defined by winding numbers, is the degree of the line bundle. So this guy here, by that kind of observation, is, well, these indices, as you see the section that we're computing here is a section of omega 1 of the base curve tensored with the index of this relative guy. So this is 2g minus 2 minus d. Okay, and that's the theorem that I stated at the beginning. You just put the delta to the other side, and the number of tangencies is less than or equal to 2g minus 2 minus d plus delta. Okay. Fernando, was it Fulton who taught that course? Or Baum? Who taught that course with the Bottom 2? Is it Baum? Yeah. Oh, it's a great course. Okay, so a couple remarks. applications. So the constant case, where E is just a fixed elliptic curve across C, and pi is just a projection on the P, is quite interesting. So I encourage you to think about this as a little exercise. In this case, the Betti foliation is just take a point of E across the curve. It's just the obvious trivial foliation on this product. And you get, if you think it through for a second, you'll get the formula quite easily. D is 0, delta is 0, and you just get 2G minus 2 points of tangency, and it's just the Riemann-Hermits formula, sorry. Okay. Two, in the paper we show that for a very general pair of an E and a point P of infinite order, there are no tangencies with the torsion sections, with E0 torsion. Right, is the union. Okay. There are going to be tangencies with the Betti leaf, but they'll typically not happen at the torsion sections because that's a countable set inside this uncountable set of leaves. Okay, the bound is sharp. We give a bunch of examples to show that this is exactly the right number. We can, not sharp, so we give examples where this is exactly what you get. And the fact that 2G minus 2 minus D plus delta, we've said that some integer, non-negative integer is less than this, so this guy better be bigger than or equal to 0, has some applications. Some arithmetic applications to heights of points. Okay. And then the last thing is an application to geography of surfaces. This is actually where the project started. Giancarlo had this idea, but needed to know some things about these intersections. So using point number 2, we construct surfaces X with the following properties. We can take the geometric genus of X to be just any fixed arbitrary non-negative integer. X has one log terminal singularity. So it's not smooth, but it's very mildly singular. Kx is Q Cartier and ample. And then the point is that Kx squared can be arbitrarily large. And that's interesting because if X is smooth, if X were smooth, then Noether's formula would give an upper bound on Kx, right? It would say that Kx squared less than or equal to 12 times PG plus 1. Okay, so if we just allow even one singular point with a fairly mild kind of singularity, that bound goes out the window. You can have an arbitrarily large volume with a fixed geometric genus.
But as n goes to infinity, the singularities approach a log canonical one?
What's that?
When for fixed G, if n goes to infinity, the singularity approaches a log canonical or something like that. The discrepancy becomes...
I think so, yeah. Yeah, let me draw the picture, and you can decide the answer to that from the picture. So the way that you get this X is that you take an E with this 0 section and a P that intersects it everywhere transversely. You blow up all but one of the points. So 0 is now here, P is here, and we've got a bunch of things like that. And then you contract, you check that the contractibility criterion holds, so then you contract P union 0, and that's the singularity. So once you think to do this, then you just make some numerical calculations, and you get all this stuff here. Okay, so that's what I wanted to say about that first foliation, the first the second two papers. One of them actually just proves the finiteness of the set of tangencies in a kind of pretty rough and ready way, and then the second one actually gives this bound using this real analytic one form eta. And now I want to switch gears and talk about something completely different. Actually, any questions about this? Because the second part is completely different.
Well, what about the Weierstrass vibrations? Do you get something more explicit?
So by which you mean, guys, where just the naive plane cubic is the good model? Yeah, so a very general guy is like that automatically. So this works in general, but if you want to consider a general E, then it will be a Weierstrass vibration. So in other words, the bad fibers will either just be a nodal cubic or a cuspal cubic without any further blowing up. There's this more complicated Kodaira. That's what you're alluding to, right? Yeah. It doesn't make any real difference for the basic theorem, but it's good for the, that's what happens for very general E's. Even general E's, actually, off the complement of an advisor.
And what about positive characteristics?
Good question. So we think the theorem is still true with the same bound, but this proof doesn't work, right? It's very, very tied to characteristic 0. We don't have any reason to believe that it's false as long as you stay away from multiples of p times n. That messes up everything, right? Because as soon as you multiply by p, if you've met a point, you're now quite tangent to it, and you can make it more and more tangent by taking higher and higher powers of p. But that's an open problem. We'd like to have a proof. I kind of like this proof, but it would be nice to have a proof also that works in characteristic p, but this one doesn't. Yeah.
What about the higher dimension family of
Also an excellent question. So there the picture is quite different. So, so if I had a family, say a one-parameter family of a billion varieties of dimension g, it would still be the case that the torsion points are everywhere dense in there, but they're going to be curves inside something of dimension 3 or more. And so what one would expect is that most p's wouldn't meet a torsion section at all, not even meet one. It doesn't help. It doesn't help because the codimension is still pretty big. Yeah, so this unlikely intersection business would lead you to expect that, in fact, for a typical A, family of a billion varieties, in a typical non-torsion section, it would never meet a torsion section anywhere. And occasionally, maybe it might meet. And to be tangent that's asking way, way, way too much. It's just a very different environment. I should have said before here that in this family of elliptic curves, the torsions are everywhere dense. So your P is meeting torsion points all the time, right? In every little neighborhood, it's meeting infinitely many torsion points. The question is it ever tangent to one of them? But that picture is completely different in higher dimensions. Okay. All right, so I won't have a lot of time, but I just want to say a few things about this other topic. Apologies to those of you who've heard it before. I talked about this here a few years ago. So the question is about rational curves. So Lang says the following. Lang made the following conjecture, that if X is the surface of general type, smooth, of course, so general type meaning that kappa of X is 2, then there are only finitely many rational curves on X. So a rational curve here is a closed irreducible subset of dimension 1 whose normalization is P1. And Lang was inspired to make this conjecture by considerations of rational points. If you have a rational curve, let's say you're over a number field, the rational curve is defined over some number field. It's a P1, it's got lots and lots of points, and that's going to contribute a lot of points. And he wants to say that a surface of general type typically shouldn't have a lot of rational points. So if you remove the rational curves, then there should only be finitely many points on what's left, rational over any number field. So that's the motivation for this, but it's really purely a geometric question. So what about elliptic surfaces? So what about if the Kodaira dimension of X equals 1, a sort of properly elliptic surface? Well, what rational curves do you have? Well, we have components of bad fibers. So I'll make a list of rational curves here. You can have components of bad fibers. right? Those look like this, or possibly like this, or things like that, where each one of the curves in the picture is a rational curve. So there's finitely many rational curves like that. You could have sections. And you might even possibly have multi-sections that could be rational. And because of the sections, there's no hope that there's finiteness here, because as soon as you have a section of infinite order, you take all of its multiples, you get infinitely many rational curves. So it's absolutely false that there are finitely many rational curves on a surface of this type. So, but there's a way to fix this. So I make the following conjecture, that if X is a smooth projective surface over C, then I take the following set. I take the canonical of X, its intersection multiplies to C. I look at these integers where C inside X is rational. So that's a set of integers. And the conjecture is that this is bounded above. So Lang's conjecture clearly applies this for surfaces of general type, because if there are only finitely many C's, there's only finitely many numbers in this set, it's certainly bounded above. The converse is true as well, though. If you bound the canonical degree of a curve of a rational curve on a surface of general type, you bound the number of them. They don't move. There can only be finitely many in each class. You bound the degree here, then you bound them. So this is equivalent to Lang. If kappa of X is equal to 2. If kappa of X is equal to 1, what this is saying is that the following set is bounded, namely the degree of the map from C to the base P1. When I say kappa equals 1, this is only interesting if E lives over P1. If the base curve has higher genus, then there's only bad fibers, and there's clearly only finitely many. So here you're looking at the degree over the base 1 where C in X is rational. So this conjecture is asking for the boundedness of this. So what it's saying is you may have some sections, you may even have some multi-sections, but you don't have multi-sections which are both rational and arbitrarily large degree over the base. Okay, and then if kappa of X is less than or equal to 0, then this conjecture is trivially true. Simply because this set is either 0 or a set of non-positive numbers. So it's certainly bounded above. So this is a reformulation of Lang that works for all surfaces at the same time and implies something quite interesting about elliptic surfaces, namely the degree of this boundedness. And I got into this because this implies a statement about boundedness of ranks of the base change of your elliptic surface to rational covers. I was trying to construct the opposite. So I think you all know I like elliptic curves of high rank, but it turns out that it's probably not possible. In fact, this conjecture says that all those constructions are going to fail. Okay, so I have no idea how to prove this conjecture, but I do have something to say about it. So the theorem, which is in that paper, the first paper that was on the reference list, is that for a very general E over P1 with kappa of E equals 1. E has finitely many rational curves. And in fact, you can say how many. It's 12D plus 1, where D is the same D as I had before. So what this is saying is that the only rational curves on this very general guy are the components of the bad fibers, each of which is a nodal cubic, and the 0 section. So there are no other rational curves on a very general guy. And the reason I bring this up at this conference is that the proof of this actually uses kind of an interesting foliation. So I'm going to give a very bastardized account of that. So you consider a picture like this where you have a base. This is a base for a family of elliptic surfaces. X is a family of elliptic surfaces. I have a base across P1. This is just a projection. There's a map I here. There's a map phi here. So what you want is that for every b and b, the fiber xb is an elliptic surface. So xb fibered over p1 with kappa of xb equals 1. The map, so this is one thing you want. The next thing you want is that the map B from the moduli of things like that is atol and dominant. And finally, for every B and B, you get a map here from B cross P1 to XB. And I want this to be a multisection and not equal to the zero section. Okay, so this is setting up for a proof by contradiction. If we did have, if this were false, if the very general guy did have rational curves besides the zero section, then you would sort of be able to write down a family like this. It's a Hilbert scheme argument. You write down all possible multi-sections, so mass from P1, and then you do a little monkey business to cut down and pass to open sets and so on to get this map to be atol and dominant. So, the dimension here is 10d minus 2. That's the dimension of the moduli space. I fixed a degree implicitly. This has dimension n plus 1. This has dimension n plus 2. And I'd like to rule out this situation. I'm going to try to copy a proof of Voisin, who's proved that a general hypersurface of high degree in projective space doesn't have any rational curves on it at all. I would like to copy that proof, but I can't because every one of my E's does have rational curves on it by definition. It has a zero section and it has some bad fibers. So I can't hope to prove that there are none. I just want to prove that there aren't others than the obvious ones. So it's slightly tricky, but there's an interesting distribution that shows up, or an interesting foliation. It's really a distribution, I guess. So in the argument, you consider sections of omega n plus 1 of x. So not top, but top minus 1 degree forms here. If I pull them back by, so let's say that omega is such a thing. If I pull such a thing back by I have to get 0 because it's a top degree form on this variety that has P1 as a factor. And that's a differential condition. To the extent that I can write down omegas, that's a condition on this map. It's saying something about that. And let me just point out that choosing a top form on X gives an isomorphism between this omega n plus 1 and the tangent of X. Right, so every time I write down one of these forms, I get some vector field, and I'm getting some information about the map I because it has to pull the form back to 0. You could work with the with the tangent vectors, but it's technically a little simpler to work with the forms. Okay, so we'd like to have lots of sections of this guy. So we compute phi lower star of omega n plus 1. Turns out to be a vector bundle. And you can write down a generating set of sections very explicitly because the deformation theory in this business is extremely well understood. I'm basically on the moduli space here. I'm atol over the moduli space, and I know the deformation theory, so it allows me to write down sections of this Wunder bundle. And then you find that these sections generate a codimension 2 subspace of this at most points. And that, in retrospect, is not super surprising. So in the Voisin argument, what you get at this point is a global generation. You compute this push forward, and you see that the sections globally generate the vector bundle. And that allows you to conclude that there can't be any rational curves at all, because any rational curve whatsoever would have to be tangent to too many things. That's not what happens here. We're in codimension 2, but that's sort of to be expected because we always have the zero section, and we always have the class of a bad fiber. And those two cycles somehow are forcing what you get in this generation into a codimension 2 thing. So, okay, that's fine. That's sort of what we expect. But then there's a real surprise. And this, I would love it if one of you foliation experts could explain to me why this happens. So the big sort of miracle here is that this distribution, let's give this a name. So we've got a distribution D here, sits inside omega n plus 1 of x, and this is essentially the same thing as the tangent model of x, right? Yeah, perfect. So the miracle is that this D has 2 first integrals. So in other words, it's kind of a trivial as a distribution, and they're familiar guys. One of them is J, which, let me write my coordinates here. So the Weierstrass form of my elliptic curve would look like this, where A and B are functions on the line, so homogeneous polynomials. So this is A cubed over 4A cubed plus 27B squared, so the J invariant. And then there's something that I call the K function, which is x times A over B. Okay, so those are 2 sort of invariant functions on the universal curve in this family. And they turn out to be, they give this foliation. I have absolutely no idea why this is. Why should these 2 canonical functions be the thing whose level sets give the foliation? But once you know that, you're in pretty good shape here, because this is enough to conclude, because you look at this picture. You have B cross P1. You have this total space here mapping to B. And then we have a map here, J and K, into P1 cross P1. And we have this map here. And the fact that these guys are first integrals for the distribution means that the fibers of this map have to have dimension at least n. And that means that the image here is actually a curve. There's a single rational curve with the property that for every one of these elliptic surfaces, the inverse image of that rational curve has a rational component. And that's totally ridiculous, because this map is highly ramified with a branch locus that's moving all over the place. So the general inverse image here is easily seen to be irreducible of higher genus. So that gives the contradiction that gives the theorem here. But the miracle somehow, which is, I think, quite unexplained to me, is why those 2 very natural functions are the thing that gave this distribution. The distribution came to us just by a kind of straightforward calculation from deformation theory. Okay, so I think I used up my time. Thank you.
Any further questions for Douglas? I have a question. So in the first part of your talk, it depended on the elliptic surface and the section. Do you have an idea of the topological type of the foliation, if there's a general, if they are structurally stable? I mean, are they the same topologically from if you vary the moduli?
Yeah, so so I have my elliptic surface over my base curve, and the foliation has leaves of 2 types. They're closed leaves, which are just the torsion multi-sections. So those are atol over the open curve, and you can say what happens over infinity. The other leaves are essentially the universal cover of the open curve, up to a finite quotient. Remember I said that the leaves were parameterized by R mod S mod gamma. If you take an RS and then take the orbit by gamma under that guy, so that's a quotient of gamma by a finite index by a finite subgroup, that sort of sub-universal cover is exactly what the leaf is. So they don't vary too much, and P doesn't know about them at all. The section that you started with doesn't know anything about the topology of the leaves.
Okay, thank you. Any further question? So we thank Douglas.
When you mentioned that J and K are first integrals, but you would like to have a reason to know why that is, but you compute it by hand. It's just by chance that you find it.
Yeah, it's just a dumb calculation.
Okay.
I mean, so what happened was I went to talk to Voisin. I said, I've constructed this distribution. I don't understand it. And she said, well, there's this theorem of Joannolu that implies that it has first integrals. And I had a little trouble understanding that theorem, but in the process of trying to understand that, I just noticed that J and K do the job. Yeah. So you just compute dj, dk, and you see that they vanish on this thing.
Any further question? So we thank Douglas again. And